Voyager did something that sounds like a physics prank. It reached the edge of the Sun's domain and pushed through a region popularly described as a 50,000 debris hell wall. And it didn't melt. Even crazier, when that crossing happened, Earth didn't find out in real time. The radio signal took roughly 17 hours to crawl home across more than 120 ADU of distance. NASA JPL Voyager mission, Stone et al., 2013. So what is this wall? Why is it there? And how can a spacecraft launched in 1977 survive something with a temperature number that belongs in a blast furnace? Stay with me here, because the answer flips what you think temperature means in space. And it's the key to understanding where our solar system actually ends. When you hear 50,000 degrees, your brain instantly builds a scene: glowing metal, roaring heat, instant destruction. But out where Voyager is, the universe plays by a different rulebook. The number can be real in a very specific way, and still not behave like heat the way you experience it on Earth. Here's where it gets crazy. The edge of the solar system isn't a single line you cross like a border checkpoint. It's a layered, shifting battlefield. First comes the termination shock, where the solar wind stops being supersonic and abruptly slows, heats, and compresses like a shockwave in a plasma ocean. Then the heliosheath, a turbulent mixing zone. Then the heliopause, the true boundary, where the sun's bubble of influence finally gives way to the surrounding interstellar medium. Stone et al., 2005, Stone et al., 2008, Stone et al., 2013, Stone et al., 2019. And if you're thinking, okay, so Voyager just crossed a neat, clean border, you're thinking like everyone did, until the data refused to behave. Impossible fact number 1. Voyager 1 and Voyager 2 didn't meet these boundaries at the same distances. Voyager 1 hit the termination shock in 2004, Voyager 2 in 2007, and not at the same location, meaning the Sun's protective bubble is not a perfect sphere. Stone et al., 2005, Stone et al., 2008. Impossible fact number 2. Voyager 1 crossed into interstellar space in 2012, but NASA didn't confidently announce it until 2013, because one of the obvious signs didn't look the way textbooks promised. Stone et al., 2013. Impossible fact number 3. Voyager 1's main plasma instrument had failed years earlier. So how do you prove you've entered interstellar plasma when your plasma speedometer is dead? That sounds like trying to prove you crossed into a new ocean with a broken compass. So what did it actually smash through? And why did the temperature out there not behave like heat at all? To answer that, we need the normal science first. Because the normal science is exactly why this story feels like a reality glitch. The sun constantly blows out a stream of charged particles called the solar wind. It's thin, but it's fast, and it drags the sun's magnetic field outward, inflating a giant bubble around our planetary system called the heliosphere. Near Earth, the solar wind is strong enough to shape space weather and make auroras dance. Farther out, it thins and spreads, but it's still moving fast, until it runs into something that doesn't belong to the sun: the interstellar medium, the sparse gas and magnetic field that fills the space between stars. When one flow meets another, you don't get a clean line. You get a complex boundary zone. At the termination shock, the solar wind abruptly slows and heats. Then, in the heliosheath, the slowed solar wind becomes turbulent, like a river turning into whitewater as it hits a boulder field. Finally, at the heliopause, the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Past that point, you're no longer inside the sun's plasma bubble in the same way. NASA Heliophysics Overviews, Stone et al., 2013. What should happen in an ideal world. You'd expect solar wind particles to fade down, galactic cosmic rays to rise up, plasma conditions to change, and the magnetic field to show a clear "you're not in Kansas anymore" signature. This is where things get strange, because the crossing was both obvious and not obvious. Voyager 1 saw dramatic changes, but one key piece didn't do the clean flip everyone expected. Debate erupted. Scientists around the world stared at the same plots and asked the same uncomfortable question. Did Voyager really leave the heliosphere? Or did it just enter a weird region inside it? Hold that thought, because here's the open loop that makes the 50,000 Regadi Hell wall make sense. Even if particles out there have energies equivalent to tens of thousands of degrees, it doesn't automatically mean they can cook a spacecraft. In fact, in terms of actual heating, that region can be closer to cold vacuum than you'd ever guess. I'll prove that in a second. Now rewind and watch the detective story unfold. Voyager 1 and Voyager 2 launched in 1977 for a grand tour of the outer planets. They delivered Jupiter and Saturn like a mic drop. Voyager 2 kept going to Uranus and Neptune. But the secret destiny of both craft wasn't planets. It was the frontier. Keep going until the sun's bubble ends. As the years passed, the solar wind weakened with distance, but it never fully vanished. Then, in 2004, Voyager 1 slammed into the termination shock. The instruments saw the solar wind slow and the particle environment heat and change. Confirmation that the heliosphere has a real, physical structure, not just an abstract zone. Stone et al., 2005. In 2007, Voyager 2 hit the termination shock as well, but at a different distance, reinforcing the idea that the heliosphere is asymmetric, squashed by the surrounding interstellar magnetic field and shaped by solar activity. Stone et al., 2008. Now the tension built. Beyond the termination shock lies the heliosheath, the solar system's stormy outer sea. Researchers watched for the signature of the heliopause, the true edge. Then, in August 2012, Voyager 1 saw a dramatic drop in solar origin particles and a sustained rise in galactic cosmic rays. That's the kind of change you'd expect if you'd crossed from mostly sun to mostly galaxy. It looked like a door opening, but the magnetic field direction didn't behave in the clean, simple way many models predicted. Cue the argument. Maybe Voyager 1 entered a new region but not interstellar space. Stone et al., 2013. Discussions in heliophysics literature around 2012-2013. And then the problem got worse, because Voyager 1's plasma instrument, the tool that could directly tell you the density and flow of the surrounding plasma, wasn't working. So how do you prove you're swimming in interstellar plasma without a working plasma meter? Here's where the science turns into a heist movie. Scientists used a 3-part forensic test, 3 clues. Count them with me. Clue 3, solar particles dropped sharply and stayed low. Clue 2, galactic cosmic rays rose and stayed high, consistent with reduced shielding by the heliosphere. Clue 1, the clincher. Plasma density jumped to values consistent with the interstellar medium. And that last clue was pulled off with a workaround so clever it feels illegal. Don Gurnett's team used Voyager 1's plasma wave subsystem to detect oscillations in the plasma, basically ringing that can be excited by shock waves from solar eruptions traveling outward. Those oscillations reveal plasma density, the way the pitch of a plucked string reveals tension. It's like tapping on a wall in a dark building and identifying the room behind it by the sound. The densities they inferred matched interstellar plasma, not heliosheath plasma. That sealed the case. Voyager 1 had crossed the heliopause. Gurnett et al., 2013, Stone et al., 2013. Now, about that 50,000-degree hell wall. What Voyager encountered wasn't a literal wall of fire. It's not a glowing barrier. It's a region near the solar system's boundary where particles can be extremely energetic, often discussed in connection with heated plasma in the Helios sheath, and, in some explanations, a hydrogen wall, where neutral hydrogen piles up and heats through charge exchange processes at the interaction zone between solar wind and interstellar medium. Hydrogen wall concept discussed in heliosphere literature, e.g., Wood et al. Lyman alpha absorption studies. So why doesn't Voyager melt? Because temperature is not the same thing as how much heat hits you per second. Temperature, in physics terms, is tied to the average kinetic energy of particles. On Earth, when the air is hot, there are an unbelievable number of molecules smashing into you constantly, transferring energy into your skin. That's heat you feel. Out at the Heliopause, the density is so low it breaks your intuition. You can have particles moving as if the gas were tens of thousands of degrees. But there are so few particles that the total heat transfer is tiny. Voyager is basically flying through an extreme vacuum with a sprinkling of very fast bullets, most of which miss. Here's the pattern interrupt that makes it click. Imagine a room labeled 50,000 Tainet Wujo. But inside that room, there are only a handful of air molecules total. Those few molecules are screaming fast, so the temperature number is huge. But there aren't enough collisions to dump meaningful heat into you. In terms of actual heating, it can be closer to standing in cold space than standing near a furnace. That's the reality-breaking lesson Voyager forces on us. High temperature does not guarantee high heating when there's almost no matter to carry that heat. And it's satisfying until it raises new questions. Because if Voyager 1's crossing was real, why was the magnetic signature confusing? Why didn't everything look textbook clean? Now we hit the second twist. Voyager 2. In November 2018, Voyager 2 crossed the Heliopause 2. And unlike Voyager 1, Voyager 2 still had a working plasma instrument, which let scientists directly measure changes in the solar wind as it approached the boundary. That gave a cleaner, more instrument-rich confirmation. Stone et al., 2019, Nature Astronomy, Voyager 2, Heliopause Papers, 2019. But the details didn't match Voyager 1. Different distances, different boundary behavior, different thickness of the transition. The solar system's edge isn't a static fence. It's a living boundary that shifts with the Sun's 11-year solar cycle and is shaped by the interstellar magnetic field pressing on it. Heliosphere modeling context. Ibex and Voyager comparisons in literature. And then there's the controversy that makes the frontier even messier. For years, many scientists expected the heliosphere to have a classic bow shock, like a supersonic boat wave, as our solar system moves through the local interstellar medium. But results from Ibex suggested we may not have a strong bow shock in the simple sense, possibly more like a gentler bow wave, depending on the relative speed and plasma conditions. McComas et al., 2012. So the fiery edge isn't one clean wall. It may be multiple overlapping effects, shocked solar wind plasma, neutral hydrogen pileups and charge exchange chemistry, and magnetic draping, where interstellar magnetic field lines wrap around the heliosphere. It's less like crossing a border, and more like pushing through layered weather fronts that change with time. And that's why Voyager's story still isn't finished. The boundary it crossed is a moving target, and we only sampled it along two narrow paths, Voyager 1's direction and Voyager 2's direction. Two needles through an enormous, shifting bubble. So I'm handing the mystery to you, because your intuition matters here. I genuinely want to know what you think the hell wall mostly is. A. primarily a heated hydrogen wall from charge exchange near the boundary. B. Primarily superheated heliosheath plasma beyond the termination shock. C. Primarily a magnetic barrier that controls which particles can enter and leave drop A, B, or C. And tell me what measurement would convince you you're wrong. I'll read the comments. Because this isn't just a cool Voyager trivia story. This affects all of us. The heliosphere acts like a kind of space weather shield, helping modulate how many galactic cosmic rays reach the inner solar system. Cosmic rays matter for astronaut radiation risk, spacecraft electronics, and understanding the environment future deep space missions will face. NASA Heliophysics Overviews, Cosmic Ray Modulation Literature. It also connects to bigger astrophysics. Every star with a wind probably carves its own astrosphere. That means these bubbles could influence radiation levels around exoplanets and potentially play a role in habitability. Voyager isn't just teaching us about our backyard. It's giving us a template for how star systems interact with the galaxy. And the future is already lining up its next move. Missions like IMAP are designed to map the heliosphere and its boundary using energetic neutral atoms, essentially imaging the frontier from the inside. And there's a long-term dream mission concept, an interstellar probe designed to reach hundreds of AU much faster than Voyager, sampling the boundary in multiple directions and finally turning our two-needle sample into a real 3D map. NASA IMAP Mission Materials. Interstellar Probe Concept Studies. Here's the hopeful part. Voyager is still out there, still whispering back data with fading power from a place no human-built object had ever touched before. The spacecraft didn't smash a wall of fire. It smashed our intuition about what hot means. And it proved the solar system has a real, physical frontier you can cross. But this isn't the only edge of the solar system twist. Next, we'll talk about how Voyager is still communicating, what its power decline means, the weird geometry of the heliosphere, and why the next probe could make Voyager look like a first draft. Thanks for watching. Keep looking up, keep asking better questions. See you in the next one.